Welcome to Center of Math's Images in Math playlist. For this video series, we're going to go over some mathematical topics that involve some pictures. Some topics we're going to talk about is the Koch snowflake, Euler's line, and Pascal's mystic hexagons, which each have some geometric content to them, and some other topics as well. And so today we're going to talk about the Koch snowflake. This is a fractal curve. This is a nice curve. So as you can see here, the Koch snowflake, as we build it up, it looks like a snowflake. We build it up inductively. We take a triangle, and then every middle third of each edge we remove, and then we kind of put an equilateral triangle on top of that removed part. And then each edge we have after that, we do the same procedure, and we just do that infinitely. And so here we will see the first 4 iterations of this process. So a few calculations we can run through. We can calculate the perimeter and area of this figure. So one quick thing we can note. So a lot of these calculations, we kind of do them iteratively, see how many we have at step n, how many will we have at step n plus 1 in terms of step n. So the number of sides, we start with 3. Note that when we remove a middle half and add 2, this one side becomes 4 sides, and the same for each other side. So really, each step, we multiply the number of sides we have by 4. And also note when we remove a middle third and put the triangle, each new edge is 1/3 the length of the original edge. So the side length of each edge will be the original side length, which is whatever we start with, over 3 at the end, so 1/3 each time. So the perimeter is just sum up the length of each side, which is just these two multiplied together, so 3s0 4/3 n. So note, as n goes to infinity, the perimeter actually goes to infinity. And a neat thing about this curve is the area is in fact finite, even though the perimeter is not. So one way to calculate the area is to note, so each time we move forward in our procedure, we kind of add the area of so many new little triangles. And so the area of the added triangles of a new triangle, note that it's built on the edges of the previous little triangles, but it's 1/3 the edge length, so it's 1/9 the area. So each time we kind of 1/9 the area of each little triangle. So the area of each triangle is the initial area over 9 to the n, the nth iteration. And we have the number of these that are added is the same as the number of edges in the previous iteration. So say this is big N, n little n is the number of sides we have. So n minus 1, this is 3 to the 4 of the n minus 1. So this gives us 3/4 a0 times 4/9 n is the amount of little triangle area we add at each iteration. And so the area of the big triangle is just you add up all these areas we add up. So we have the initial area, which we're calling a0, plus sum k equals 1 to infinity of all these little triangles. And if you sum all this up, you'll get it's equal to a0 times 8/5, which is finite. So this figure, in fact, has finite area, an infinite perimeter, but finite area. So now this image, we can see that something else that's neat about this figure is it's fractal. So if we keep zooming in on the edges, we keep kind of getting the same shape as we get closer and closer. The same shape will keep popping up over and over again. And something else we can prove, which I believe was in the original paper that brought this curve, brought this property of it, that this has no tangents to it. So we can't really put a line on it. That just will be tangent to the curve in the usual sense. So one other neat property of the snowflake is, so now this image, if you set up kind of 3 big ones and a bunch of little Koch snowflakes around each other, you can get a tiling of the entire plane with these snowflakes. And so yeah, that's one other thing we can do with this snowflake.